Hi there, and welcome to the Screencast of Lab 3 for 193301 Veterinary Biostats. So, today we're going to be looking at some data on donkeys in Morocco. I'm going to start by just putting my name in the author list there. And so this is from this paper here, estimation of the live weight of body condition of working donkeys in Morocco. You could Google that if you wish to have a look at the publication. And data is collected on 386 donkeys in Morocco, and a bunch of measurements are taken. So we know the sex, we know the age, the body weight, the heart girth, umbilical girth, and length and height. And the goal really is to see if we can infer the body weight. So can we estimate or predict what the body weight would be given the other variables? And the idea being that weighing a donkey requires scales, right, which is not an easy thing to transport around, okay? And so it would be useful if you could use very simple things that are other variables that are simple to measure, such as girth, for example, or height, which you can just measure with a tape measure, which is very easy to transport around. And if we could use that perhaps with a formula in order to generate what we think the body weight should be, given those other variables, then that would act as a good proxy for what the body weight is, and therefore, if we know the body weight, perhaps also the body condition as well. Okay, so we're going to read in this data. We'll run this set of code here and take a look at it. Okay. And so we can see that there's all of these variables here. We've got the age, which is numeric and ranges from 1 year old to 16 years old. We've got the body weight, which ranges from 52 kilos to 222 kilos. We've got the heart girth, the umbilical girth, the length and the height, which again are all numeric measures, and so they've been summarized in the usual way. And then we've got sex, which has been read in as a character string. Okay. Right. So we're going to start by producing some histograms of the variables in the data, just to get a feel for how they're distributed. Okay, so here's the distribution of age. Okay, we could perhaps mess a little bit around with the number of bins. Let's try 10 bins and see what happens. Okay, fairly dramatic change, isn't it, from 9 to 10? Let's do 9 again. In fact, let's do them both. I'll copy and paste, and we'll do both in the same block, and we'll just run them both, and we'll get the two plots that we can switch between. And you can see that, your conclusion between these two plots is vastly different, isn't it? There seems to be basically very few donkeys with age 5, which is interesting. Much more likely to be 4 or 6. Okay, and we don't see that at all in this plot here, because 5 is actually subsumed into the same bar as 6. And this is something that often happens when you have numeric data that is rounded, right? So we have the age just to the nearest year. Okay, so all the values, if we look in the data, all the values are just whole numbers. And you can see as I scroll down, there's very few 5s, right? There's one there. I think I just went past one. Maybe. Oh, there it is there. Okay, so there's very few 5s. A lot of them are 4 or 6, and so and that may be an importing thing, perhaps, or so it may be that just when donkeys arrived in Morocco, perhaps, we don't know. But when data are sort of whole numbers or rounded to whole numbers like that, then you've got to be quite careful with histograms, which are really designed for continuous data, so data that allows any value even between the whole numbers. In terms of the number of bins. So you've got to choose one that really gives you a sense of the distribution. I don't think this is really gives you an accurate sense of the distribution. We're not really concerned that there's actually only a handful of donkeys that are 5 years old. Really what we're looking at is the general shape, which is given a little bit better by that one. So it's just something to think about. We could perhaps add some more histograms for the other variables. So let's have a look at the body weight. And the length and the height. So instead of age, I'm just going to put the body weight in there. Body weight the length, and the height. There's a capital H, and we'll run that. And there's the distributions of those variables. Okay, so you can see that the body weight is reasonably symmetric, maybe very slightly skewed to the right, but nothing to really be concerned about. Okay, it's mostly symmetric, the same with the length and the same with the height. And we do notice that there's perhaps a little bit of an outlier here. There's a big gap, isn't there, between these, and it only looks as though there's maybe only one or two out at this value. So that's perhaps something to look into further. But otherwise, the distribution seems to be mostly symmetric. Let's increase the number of bins on that one maybe and have a look in a little bit more detail. Okay, yeah, so you can see that the vast majority are down here, and you just have perhaps one donkey up here that is very, very tall for some reason. Maybe it's a horse. Okay, right, so let's add some quick notes about these. Okay, let's get all the graphs back. Okay, so the distribution of body weight, length, and height are mostly symmetric. Body weight ranges from 50 to 220 kilos. Let's just flick back to that and have a look. With most around 100 to 150 kilos. Length ranges from, that's probably about 60 to 120 centimeters, with most around 70 to 90. And height ranges from, what's that, that's probably about 75 to 120. Mostly with one or a couple of very tall donkeys. Okay, so just general comments is what we're after, just like we did last time. Don't get too concerned if there's very slight evidence of skew and things like that. You can obviously mention that it's very small, but generally, just sort of general comments is what we're after. Okay, now to have a look at a little bit more detail at that outlier there, let's do a scatter plot instead. So we're going to data equals donkey. We're going to do a scatter plot, so we're going to be using the points, and we're going to map x to the height and y to length. Okay, so now we can see that this is very clearly an outlier, right? It's way away from the rest of the data. So this donkey horse with outlying with very large height and large length seems to be very strange. Okay, maybe this was recorded incorrectly. We don't really know, but maybe we should think about taking it out. So the first thing we have to do is figure out which one it is, right, in order to take it out. Well, we don't have to do that to take it out. We could subset the data using code to get rid of it. But let's see if we can find it anyway, because it's a useful sort of thing to be able to do. So if we click on the data set, then you could just scroll through and find the one with the very large height. There it is right there, 179. Of course, it's much easier if you sort by height. So if you just click on height once, it'll sort it by height, and we could scroll down, or we could click it again and it'll sort descending. And then you can see that it's donkey number 52, isn't it? Who is a male, age 14, has it's quite heavy, and has that very large height. Okay. Right, so on the data set and sorting descending by height shows that it is donkey number 52. It has the large height, 179 centimeters. So we could find this and remove it with code by subsetting the data. Okay, so we're going to use the subset command. So subset our donkey data set, and then we just have a condition that we want to use. So for example, if we wanted to find it, we could pull out any donkey with height bigger than 140, right? So if we look at our plot, there's only the one that's bigger than 140, right? There's 140 there. And so subsetting the data and pulling out just donkeys with height more than 140 will give us that donkey. And of course, if we want all of the donkeys other than that one, we can just reverse the condition, right? So we could just go subset donkey where the height is less than or equal to 140, right? That's the opposite of, right? And so when we do that, we'll get 385 rows, right? And the original data set had 386 observations. So we've removed one, right? So now we want to be able to save the output from that. So when we ran that, it just spat it out, right? It just printed it out, but we don't have it to reuse, right? We've just got the original donkey data set. So to save it, we want to assign it to a new variable. So let's make a new one that says only donkeys, right? When I run that now, because it's an assignment, I won't get any output by default, right? It hasn't printed out the outcome of that, but we have got our thing up here, right? So we can click on that and we can see that if we sort by height again, then the largest one is now 126, not 179. Okay. Right, now we could check that worked, of course. I mean, we've already checked it, but another way to check is just to redo the scatter plot. Right, so we just redo the same scatter plot we did before. Let's run it to make sure it still works. Yes, and now we can just change the data set from donkey to only donkeys. And there it is there. Okay. Right, so you can see, maybe we can write a little bit about this one. What could we say? Well, as predicted, as the height increases, the length of the donkey also increases. Right, the trend is a positive straight line relationship. Right, you can imagine a line going through here that most of the points are following, obviously with some scatter, the scatter being the individual donkeys. You know, it's not going to be a perfect relationship between height and length. Some will be taller than you would expect given the length, and some will be longer than you expect given the height, right? But that's the general trend is there. We could also investigate the relationship between body weight and sex. Okay, so to do that, because sex is a categorical variable, we're going to start with the only donkeys data set. And because sex is categorical and body weight is numeric, then we might want to use maybe a box plot. Right, so we could use a box plot to describe the body weight and change the Y by sex. Or we could just change the colour by sex, couldn't we? That would work too. There we go there. Notice that if I don't tell it what Y is, it just kind of puts an arbitrary axis here, which is completely meaningless. Okay, so it's often helpful to put Y in as well. Okay, so that your axis is somewhat useful. The guide here, of course, is now no longer useful, really. I mean, because we already know which one's male and female from the axis, but it's not too bad. If you do want to turn the guides off, you can just go guides, and then you turn off the color guide. So the color equals none. We'll turn the color guide off. Okay, guides can be used to change the guide in some way if you want to, to mess around with how it looks and stuff. But mostly we use it just to turn things off. Okay, so there we go there. And so our conclusion from this is that well, what would it be? It would be, there doesn't seem to be much of a difference, is there? Male and female donkeys. The distributions are mostly symmetric, centered at around 120 kilos, with most between 100 and 150 kilos or so. Range is from 50 up to 220. Right. Okay, and finally we might want to look at scatter plots. So, because the purpose of this exercise, the purpose of the data being collected was to estimate the body weight from the other variables. We can see that using the sex here by itself is no use, at least. But presumably the measurements might be of use. So this is the body weight versus measurement variables. Okay, and we could use scatter plots for these, couldn't we? We've got two numeric measures. So we could use John Point for a scatter plot. The mapping is going to be, we can make x so what have we got? We've got what variables do we have here? We've got the heart girth, the umbilical girth, the length and the height. So let's have a look at length first. Put the body weight on the y-axis. So there we go. Okay, and then we'll just change to the other measures. So we've got the height. There's the height graph. We've got the heart girth. And we've got the umbilical girth. Okay, I'm just looking in this here to find out what the variables are. Okay, so all at once so that we can see them all. Okay, so as you would expect, each of these graphs have a increasing trend. Right, so as the measurement variable on the x-axis increases, the body weight on the y-axis also increases. Right, as donkeys get bigger, they weigh more. Right, so this is pretty sort of standard stuff. So let's write that down. So as the measurement variables increase, the body weight also increases, as expected. As donkeys get bigger, they get heavier. Right, this is pretty straightforward stuff. The relationships are mostly straight line, aren't they? Mostly straight line. Would you describe those as straight line? I think so. Near enough. Maybe some slight curve in some of them, but generally straight lines. Right, so you're basically looking to see if, is the obvious curve there. The other thing that we might want to look at is, are there any unusual points? Maybe this one might be a little bit unusual, do you think? This one here seems to be a little bit heavier than what we'd expect, given the height. So given the height, we'd expect it to be down here with these others, wouldn't we? So it's a little bit heavier given the height, but maybe it's just a short fat donkey, maybe. These ones are all mostly okay. This one has much more spread, but there's not really any really out on their own, so I think there's not really too many unusual points there. Lots of variation around the trend lines, and that then gets us to a comment on strength. So if you look at these, have a think about which ones show the strongest relationship, and what do you think I mean when I'm talking about the strongest relationship. And really what you're looking for is which of these variables would be the best to predict the body weight. So I think that it's not this one, right? So the reason I say it's not this one is that if your umbilical girth is somewhere between 110 and 130, then there's a huge range for your possible body weights, right? So the strength of the relationship isn't particularly large because umbilical girth doesn't tell you much about body weight. Whereas if you look at heart girth, the strength of the relationship is very high because the amount of scatter around the trend is much smaller, right? The points are tightly clustered around that trend. So once you know the heart girth, you know quite a lot about the body weight, right? You've got a very small range, comparatively speaking, to what the heart girth is. So to evaluate strength of relationship, you're looking for how tightly clustered the points are, individual donkeys, around the average trend line. So if points are tightly clustered, then it's a strong relationship. Knowing the X value tells you quite a lot about what the Y value is. It restricts the range of values Y can take. A weak relationship doesn't constrain the Y value as much as X changes. Right? So what you're looking for is you kind of compare sort of the amount of variation in the body weight, before you know what the heart girth is, the body weight could be anywhere between 50 kilos and 220 kilos, right? That's what the range of the body weight is. But once you know the heart girth, that range is much reduced, right? So if I say the heart girth is, say, 120, then it looks as though the body weight can be between about 125 and maybe 160 odd, right? So the range is reduced from 50 to 220, which is like 170 units, down to 125 to 160, which is only sort of 35 units. So I've restricted what the body weight can be quite a lot by knowing what the heart girth is. So that means that the strength of the relationship between heart girth and body weight is very high. So heart girth tells me a lot about body weight, right? So if I'm using these variables to predict what the body weight is, I'm going to be going first and foremost for the heart girth because that will tell me, that will give me the best prediction, right? So heart girth will give the best prediction as to what the body weight is as the allowable range of body weights for a given heart girth is smaller than the allowable range of body weights for the other variables. Okay, that's the idea. Let's nip that document just to make sure it all works and gets our final HTML. That looks alright, doesn't it? There's our distributions. There is our data with the outlier gone. And here's each of our scatter plots and our writing at the end, so that looks fine.